is the function given below continuous / differentiable at x equals 1. And they define the function g piecewise right over here. And then they give us a bunch of choices. Continuous but not differentiable, differentiable but not continuous, both continuous and differentiable, neither continuous nor differentiable. And like always, pause this video and see if you could figure this out. So let's do step by step. So first, let's think about continuity. So for continuity, for g to be continuous at x equals 1, that means that g of 1 must be equal to the limit as x approaches 1 of g of x. Well, g of 1, what is that going to be? G of 1, we're going to fall into this case. 1 minus 1 squared is going to be 0. So if we can show that the limit of g of x as x approaches 1 is the same as g of 1 is equal to 0, then we know we're continuous there. Well, let's do the left and right-handed limits here. So if we do the left-handed limit, and that's especially useful because we're in these different clauses here as we approach from the left and the right-hand side. So as x approaches 1 from the left-hand side of g of x, well, we're going to be falling into this situation here as we approach from the left as x is less than 1. So this is going to be the same thing as that. That's what g of x is equal to when we are less than 1 as we're approaching from the left. Well, this thing is defined and it's continuous for all real numbers. So we can just substitute 1 in for x and we get this is equal to 0. So far so good. Let's do one more of these. Let's approach from the right-hand side. As x approaches 1 from the right-hand side of g of x. Well, now we're falling into this case. So g of x, if we're to the right of 1, if value is greater than or equal to 1, it's going to be x minus 1 squared. Well, once again, x minus 1 squared, that is defined for all real numbers as continuous for all real numbers. So we could just pop that 1 in there. You get 1 minus 1 squared. Well, that's just 0 again. So the left-hand limit, the right-hand limit are both equal 0, which means that the limit of g of x as x approaches 1 is equal to 0, which is the same thing as g of 1. So we are good with continuity. So we can rule out all the ones that are saying that it's not continuous. So we could rule out that one, and we can rule out that one right over there. So now let's think about whether it is differentiable. So differentiability. So differentiability, all right. Differentiability. Let's see, that's a long word. Differentiability. All right. Differentiability, what needs to be true here? Well, we have to have a defined limit as x approaches 1 for f of x minus f of 1 over, oh, let me be careful. It's not f, it's g. So we need to have a defined limit for g of x minus g of 1 over x minus 1. And so let's just try to evaluate this limit from the left and right-hand sides. And we could simplify it. We already know that g of 1 is 0. So that's just going to be 0. So we just need to find the limit as x approaches 1 of g of x over x minus 1, or see if we can find the limit. So let's first think about the limit as we approach from the left-hand side of g of x over x minus g of x over x minus 1. Well, as we approach from the left-hand side, g of x is that right over there. So we could write this, instead of writing g of x, we could write this as x minus 1. X minus 1 over x minus 1. And as long as we aren't equal to 1, this thing is going to be equal, as long as x does not equal 1, x minus 1 over x minus 1 is just going to be 1. So this limit is going to be 1. So that one worked out. Now let's think about the limit as x approaches 1 from the right-hand side of, once again, I could write g of x minus g of 1, but g of 1 is just 0. So I'll just write g of x over x minus 1. Well, what's g of x now? Well, it's x minus 1 squared. So instead of writing g of x, I could write this as x minus 1 squared over x minus 1. And so as long as x does not equal 1, and we're just doing the limit, we're saying as we approach 1 from the right-hand side, well, this expression right over here, you have x minus 1 squared divided by x minus 1. Well, that's just going to give us x minus 1. X minus 1 squared divided by x minus 1 is just going to be x minus 1. And this limit, well, this expression right over here is going to be continuous and defined for sure all x's that are not equaling 1. Actually, well, it was before it was this, x minus 1 squared over x minus 1. This thing right over here, as I said, it's not defined for x equals 1, but it is defined for anything not for x does not equal 1, and we're just approaching 1. And if we wanted to simplify this expression, it would get, this would just be, and I think I just did this, but I'm just making sure I'm doing it right. This is going to be the same thing as that for x not being equal to 1. Well, this is just going to be 0. You could just evaluate when x is equal to 1 here, this is going to be equal to 0. And so notice, you get a different limit for this definition of the derivative as we approach from the left-hand side or the right-hand side. And that makes sense. This graph is going to look something like, we have a slope of 1, so it's going to look something like this. And then right when x is equal to 1 and the value of our function is 0, it looks something like this. It looks something like this. And so the graph is continuous. The graph for sure is continuous, but our slope coming into that point is 1, and our slope right when we leave that point is 0. So it is not differentiable over there. So it is continuous but not differentiable.